So this is a third video of this series. We're going to be looking at determining molar mass of a gas. So this is one of the bigger lab that we have done that we didn't do a write up on. Okay, so in this case, if you go back to Blackboard in my class, you would have noticed, it is actually the copper carbonate lab. So if you go to that one, you should come to this handout, which blah, 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 like this. Now, if you hopefully, you might look at this diagram, it's like, oh yeah, we did this lab. Yeah, that's one which you have to heat the copper carbonate and it turns to color. Now it turns a little bit of color. We only collect the gas in the eudiometer up to a certain point. You have to make sure that you take this whole thing out and then before you remove it, blah, blah, blah. So that's how the procedure of the lab goes. Now, in terms of the calculation itself, it's actually quite nicely laid out. So even here, it talks about a number of things. So let's go to my setup again. So it is really based on the ideal gas law. Okay. So remember, this lab is about talking about finding the molar mass of the gas. Okay, based on an experiment. So it is a PV equals nRT. It's based on the ideal gas law. Temperature is the room temperature at the time. Okay, room temperature at the time. So yeah, temperature of the room. Pressure, that's based on the pressure of the room. Okay, room pressure, atmospheric pressure of the day. Now, volume of the gas, that's based on from your gas collecting tube, how much gas you collected. So either if you didn't have any air bubble, you'll go from you'll just do your final reading, or some of you, I've kind of said, oh, just make sure there's a bubble up to a certain point so you can do like final minus initial. Okay. So in this case, you can do it that way. So in this case, um, this is this is experimental data, and now the mole part. Keep in mind is this: you're gonna have to convert this formula. Mole is mass divided by molar mass. So we use that to substitute this whole thing in here. So you end up having PV equals RT divided by molar mass. And if you rearrange this whole thing, you isolate the molar mass this way, put it on that side. So you end up having PVE here, molar mass here. So we said this is room temperature, room atmospheric pressure of the room. This is experimental data. Experimental data, air pressure of the day. Now the mass here is actually the mass loss, because keep in mind when you do this, you put in a certain mass. Now I know the handout say 0.4, but we worked it out and we told you like do 0.2, 0.3, and then you heat it until a certain part, and then afterwards you stop the reaction when it's 3/4 of the way, and then you weigh this whole entire thing to find out the mass loss. So this is actually the mass here is based on the mass loss. Okay, because the reaction, just like on the top here, that's given to you, it is copper carbonate turning into copper oxide, and CO2 is a decomposition reaction. So in terms of the stuff inside here, you will still have a mixture of copper carbonate. You'll have that is not heated. You have some copper oxide that is formed, but the mass loss is entirely of CO2. So in this case, um, you can tell the difference. So you can use this to calculate the molar mass. That's how you do the calculation. In terms of errors and percentage errors and things like that, I've given you all this. I've shared that through Power with you all. And I asked you and your class, when someone from a classmate, to go over that together, because molar mass, except the molar mass of CO2, this is about 12.01, this is about 16. So from the periodic table, P table, molar mass of CO2 will be about 12.01 plus 32, which gives you 44.01. So whatever your calculate experimental calculation based on this, you can find the percentage error. And now, in terms of systemic error, look over what you have done with your classmate. Make sure you talk about its systemic error. Um, how does it influence the result? What are the ways you could do to reduce the impact? Now, if you look at this diagram right now, and especially if you remember your experiments, um, I'll say a couple of things. Uh, this hose here this hose here, if you remember correctly, some of you had a really long hose and it didn't really quite work out. So the length of this gas collecting tube would be an issue, because keep in mind, you have to generate enough gas to push it in. Um, this to push it in. So in this case, if you have a lot of tubes, you might not generate quite enough gas to push all the gas down here. Also, another thing is, we are assuming right now these gas, like this is not necessarily CO2. This is just plain air. You're assuming that the CO2 would actually not. Uh, we're assuming that you right now we're making an assumption that one liter of air and 1 liter of CO2, this will come up to 2 liters. Okay, you're assuming that will be 1 to 1. We are not sure if there might be an off chance that is like, some of you might have seen this demo before, like 1 liter of water to 1 liter of rubbing alcohol. It actually go to less than 2 liters, because some of the particles of the rubbing alcohol goes in between the particles of water. So in this case, we're assuming that it's going to do that. We're not sure. And chances are this, based on how we have done this experiment, where it's not like we're producing gas, pushing CO2 to a bubble, and then we'll put it in, then you can potentially reduce that. Now, if you're not quite sure what I was talking about here, come and ask me in class. But I'm just going over right now what are some of the quick things that I think about. Maybe I missed some of the stuff. Maybe you and your partner might have thought of some ideas. Um, yeah, talk to me. Okay. I'm gonna probably make the next 2 video at school tomorrow.